base, conjugate base, conjugate acid. And then here we have the acid and the conjugate base. The base and the conjugate acid. All right. Looking at pH now, just like in lab on Tuesday, we've got some laundry detergent that is pH of 9.4, that makes it basic. Some honey, pH 3.9, that's acidic. And then this is the trickiest one. Hydroxide ion concentration of 1 times 10 to the minus 5 molar. Is that acidic or basic? Basic. It's basic. How do you know? Okay, one at a time. I didn't get any of that. Somebody want to?
This concentration of OH, we need concentration of pH.
Yeah, so we use, this is the concentration of OH, hydroxide, so we can get the POH is 5. And then the pH must be what? 9, yeah, 14 minus 5 is 9, and so a pH of 9 is basic, so this is basic. And whoops, write a balanced equation for the neutralization of sulfuric acid by sodium hydroxide, so you had to know some naming of the acids here. Sulfuric acid is H2SO4, and sodium hydroxide is NaOH. Those react together to neutralize, and if it's a neutralization reaction, that means you form water. And what's left over is the sodium and the sulfate. So the sodium has to go with the sulfate, and we have to make sodium sulfate, which is Na2SO4. All right. So we have added these acid names in based on this chapter, but something like sodium sulfate, got to make sure you know those ions and know how to put those compounds together. Every quiz, every exam, always going to be there. So please keep working on that. And that was the quiz. Oh, balance. That's right. It's not balanced. Thank you. So we have to balance it. I'm going to put a 2 here and a 2 here. And it doesn't matter what order you put the reagents in. You could have NaOH plus H2SO4, or Na2SO4 plus H2O. As long as you've got the ones on the same side, they should be on the same side. Questions about that? Good. Okay. Let's move on. So on Tuesday, we talked about nuclear chemistry and some of these new kinds of ways of thinking of reactions, alpha decay and beta decay. We're going to add a couple more reactions to that list today and then talk about another part of nuclear chemistry, which is how quickly things decay and then what does it mean to be exposed to radiation in different amounts. The third type of particle or radioactive emission that we're going to talk about is called gamma rays. So we talked about alpha and beta, and this is gamma. Oops. Gamma rays, that's the Greek letter gamma. Gamma rays are high energy light. They are not a particle, although sometimes we think about light in terms of particles called photons. But it's just energy, high energy light that is radiating from a source. So when we write a reaction about producing gamma rays, it's a little bit weird because we're not actually changing any mass. Light doesn't have mass. So gamma rays can't make the numbers change in the reactions the way that the alpha and beta particles did up here. Because of that, we write a gamma particle like this. We just use the letter gamma, and then we put 0 and 0 for its two numbers, because it doesn't have charge, it doesn't have mass, it's just light. And when we write an equation for gamma decay, it looks like this. So here's gamma decay. We take a nucleus, in this case technetium 99M, so it's going to be 43. And we haven't seen that little m before by the atomic weight, or the atomic mass. That m stands for metastable. Meta means like partway, partially stable. So that means that this nucleus is not totally stable. There's something unstable about it. And that instability will manifest itself in it releasing energy spontaneously. So when it returns to the stable form of just 99, it releases a gamma ray. So no masses have changed, no numbers have changed. And whenever you see that little m, for our purposes, we're going to assume that that means that there's gamma decay involved here. Because we can't clearly say like, okay, here's a particle, here's its mass, and here's how we're changing the numbers. So numbers don't change. We just lose the little m as it goes from a higher energy state to a lower energy state and emits a gamma ray. Now, gamma rays are interesting because they're just light, which means they are what we would say highly penetrating, like X-rays. They go through stuff. We talked about how alpha particles are big and heavy and blocked by just even a little bit of air. Beta particles go a little further, but they're still blocked relatively easily. Gamma rays are really not blocked, very difficult to block. And we're going to see this when we do our nuclear chemistry lab. We're going to switch the order around a little bit. I'll tell you about that in a minute. But when we do that nuclear chemistry lab, you'll see how gamma rays can go through aluminum, even lead, even relatively thick lead. Gamma rays get right through. And that's good and bad. It's good because it means that they're so small that they're passing, I mean, they don't even have mass, but they pass right between the space between the nucleus and the electrons. So that's fine because it means mostly gamma rays just go through us and don't cause any problem. But because they're so high energy and so deeply penetrating, if they happen to knock something off, they can knock something off anywhere through your body, and it's very difficult to protect. So high energy gamma ray source or high radioactive sources that are extremely active, that are extremely intense and giving off lots of gamma rays are really dangerous because now the probability that one does something bad to you goes way up. So gamma rays are one of the biggest dangers from things like nuclear bombs and nuclear accidents when you have this massive radiation of gamma rays coming off. But they can be used for really beneficial purposes in smaller amounts. So one thing they talk about in your book are radio imaging. Now this is a little bit different. This is iodine, which is a beta emitter. But that TC99M, technetium, which is a man-made element, we produce that in huge quantities, relatively speaking, for use in medicine. Because what you can do is you can give somebody some of that radioactive isotope. And it goes to various places in your system because it's just a tiny little atom. So whatever processes in your body uptake these metals, it goes to those places. But while it's at those places, it's releasing gamma rays. And because gamma rays are so penetrating, they come out of your body. And you can use a device to scan your body and see where those gamma rays are coming from. So in that way, we can get pictures like from the insides of organs. Something like an X-ray, you can only really see the outsides, and they're great for that. And part of what's inside depending on the density. But with gamma rays, you can really put isotopes inside parts of your body and get information about where they're going, what's taking them, are they going where they're supposed to go, are they going where they're not supposed to go. In this case, this is a thyroid image with radioactive iodine. Iodine goes to your thyroid, that's why we need iodine, that's why we have iodized salt, that kind of thing. The iodine gets taken, radioactive iodine gets taken to your thyroid, and then you can scan the thyroid and see, is it going to the right place? Is the thyroid overactive, hyperthyroid, or underactive, hypothyroid? And you can figure some of this stuff out with that imaging. Another cool use of gamma rays, there, that's also a little bit kind of sad, a sad story, is radiation with food. Have you heard of irradiated foods, irradiated vegetables and meats, things like that? It was kind of in the news a lot, probably, I don't know, 10 years ago or something. You can pass gamma rays through foods. It's a cobalt-60 or cesium-137, which we'll have up in lab when we do that. You can pass the stuff through foods and knock out and kill all the bacteria in the food, which is really important for things like foodborne illness. Foodborne illness is really dangerous. CDC estimates about 1 in 6 people get sick, 128,000 hospitalized, and 3,000 die of foodborne illness, that's food poisoning, every year. This is really an effective way to prevent that. If you have your food if your food is irradiated, there's no bacteria left in it. So even if you have poor preparation techniques or cross-contamination or whatever, you're not going to get sick because the bacteria is not there anymore. The problem with it is that people are afraid of radiation. People see that, oh, this is like nuclear radiation in my food, gamma rays in my food, that's really dangerous, that's scary, I don't want that. And so people are reluctant to buy irradiated food. But actually there's no danger because the radioactive material never ends up in the food. Exposure to gamma rays does not make you also radioactive. It's the thing that's producing the gamma rays that's radioactive. So the gamma rays pass through the food, kill the bacteria, but there's nothing actually radioactive about the food itself because the source is far away from the food. So it simply has killed the bacteria, and then it's the same as it was before. But because people are so afraid of anything that sounds like nuclear or sounds like radiation, they've had a lot of trouble getting this stuff sold. Specifically, it has to carry this label saying that it's been irradiated, and so people see that and kind of get scared off and don't want to buy that. But if it kind of comes back and if it becomes more popular, it's something you should seek out, because even if there were small risks from potentially irradiated food, like if some of the molecules in the food were damaged through the radiation process, it's got to be safer than food poisoning. I mean, that's like a known killer. That's a known danger. So if you see that kind of thing, seek it out because you know more now and you know that it's not dangerous. But people feel that way about like microwaves. Sometimes people say that, oh, you're going to nuke my food or something like that, that the microwave does something dangerous, which it doesn't. It just heats it up. And it's really the same thing with the gamma rays. The gamma rays are heating up locally little bits of the food, which are the bacteria in the food. So that's another use of gamma rays. All right. So those are our 3 major reactions. There are a whole bunch more ways that nuclei do weird stuff in nuclear reactions. We're going to focus on just those for now. Our last reactions are going to be the reactions that produce the most energy. That's nuclear fission and nuclear fusion. Let's take a look at those. Nuclear fission is what most people refer to as splitting the atom. So you're breaking a nucleus apart in fission. And that releases a tremendous amount of energy. And this is the reaction that's used in nuclear power plants and nuclear bombs and stuff like that. So got a few parts to it. Rather than draw it out, I want to grab a picture from the book where they have it nicely described here. All right, so take a look at what's going on here. Here's the reaction as we'd write it on paper, and then here's kind of a picture of what's happening. This very specific isotope of uranium, uranium-235, gets bombarded with neutrons. You can actually take neutrons, you can accelerate them, and you can shoot them at a sample of uranium-235. The neutron gets absorbed into that nucleus, creating an unstable uranium-236. And this is very specific to this isotope and a couple others of plutonium and a couple other ones. But most things don't do this, so this is kind of a special weird case. The neutron gets absorbed by that uranium, and then the unstable nucleus, instead of just like spitting the neutron back out, actually splits apart into new nuclei. And the most common ones, the ones that we tend to hear about, are this isotope of krypton and this isotope of barium. It does some other stuff too. It can split into some other nuclei also. In doing so, it also releases 3 more neutrons. So 3 individual neutrons. That's special about this at all. So again, as well. So there's a couple special things. One is just that it takes this neutron and then splits apart, but also that it releases more neutrons when it splits apart, which means that those neutrons it releases can then go get more uranium-235 and continue this reaction. And that makes it a nuclear chain reaction. And that's really why it's so powerful. We don't have to keep, a big apparatus that shoots neutrons at things every time for every atom we want to split. It will sustain itself through the neutrons that it releases through this chain reaction. And so I think there's another picture of this too. So it kind of keeps going and going, and you can see, this won't even fit on one page, but you can see those 3 neutrons can go get 3 more uranium nuclei, and then they split up, and then they cause 3 more neutrons, and so this whole thing like goes and goes and goes and goes, and that's why, you can have something like a nuclear bomb. In a nuclear power plant, this reaction is also going on, but what we do is we sequester those uranium nuclei, so we don't allow the neutrons to have access to uranium, to more uranium fuel. And so it kind of slows down the reaction so we can control the reaction in that way, rather than just kind of let it go with all the fuel. So that's fission. If you look at the reaction here, the numbers still all add up. So you've got 92 on the bottom, adds a neutron, so that doesn't change the atomic number, and then you've still got 92 on the bottom when it breaks up into these two. 235 on the top becomes 236 when it grabs a neutron. And then you've got 91 and 142, which is 233. And then 3 more neutrons makes the 236. All right, so a large amount of energy comes out from that. The opposite of nuclear fission, which also releases even more energy, is nuclear fusion. This is atoms coming together. And there's various ways this is done, but one example is 2 hydrogen nuclei, hydrogen 3, which is an isotope of hydrogen, come together to form a helium atom and a neutron and a lot of energy. This is the main reaction that's happening in the sun. This is what powers the sun. These hydrogen atoms coming together to form helium. Now this is, of course, much more efficient, much higher energy, and much more efficient. We don't have to make these crazy huge isotopes to deal with to still get all this energy. So if we could use nuclear fusion in things like power plants, it'd be great. We wouldn't have any nuclear waste. Everything would just be clean, and we'd have like as much energy as we could ever possibly use. The problem with this is to get it to work, you need to be at about 100 million degrees C. That's pretty hot. It takes so much energy to get to 100 million degrees C that it actually ends up costing more energy than you get back to try to set up a reaction like this. So it's not efficient, because you have to put in more energy than you get out. The only time we really see nuclear fusion in use is something called a hydrogen bomb. If you've heard of that, that's this reaction. And this reaction actually has to be powered by a fusion reaction. So you have to have a big fusion bomb, regular nuclear bomb, just to get this thing started, to get to those 100 million degrees to get this thing started. So for power generation purposes, this is not yet practical. It's one of those things that scientists think, if somebody ever figures that out, it'll like solve all the world's problems. So why don't you guys get on that and let me know if you figure it out. I'll make an exception to my extra credit policy if you figure out nuclear fusion. Solve all our energy problems. So that'd be pretty cool. All right, so those are our reactions. We've got alpha decay, beta decay, gamma decay, nuclear fusion, and nuclear fission. And as we see, they're very different from any other kind of chemical reaction, kind of their own thing, these nuclear reactions. So now, last 2 things we're going to look at are exposure to radiation and then half-life. Exposure or measuring how much radiation we've got. There are a couple ways to do that. First way to do it is to measure how much is coming off, how much radiation is being emitted by something that's radioactive. So I've got the stuff. How much radiation is coming off of it is what that's asking. The units that we use for that are Curies, after Madame Curie, or Marie Curie, who discovered radium, and becquerels, after another scientist, Henri Becquerel, who also discovered some radiation. These are measures of like how much radiation is coming off. So if you were doing some radiotherapy or something and you wanted to have a particular amount of radiation that you used, you'd say, okay, well this particular procedure requires 40 millicuries of radiation. So you get your isotope, you figure out how much radiation is coming off of it per however much time, and you say, okay, I guess that means I need about 5 grams, or that would be a lot, 5 milligrams, whatever it is. But you figure out how much radiation you need, and this would tell you how much radiation something gives off. More important to those of us who aren't actually working with these materials so much is exposure. But we can also measure, instead of how much radiation is emitted by these things, we can measure exposure. How much radiation have I absorbed? That question would be, so absorbed by our tissues or whatever. And there's 2 units that we'll see mostly for this. One is called the rad, stands for radiation absorbed dose. And the rad tells us the amount of radiation absorbed by 1 gram of stuff. Whatever it is, a gram of it, how much radiation is absorbed. So could be some wood, could be your finger, could be a person, could be an animal, whatever. Per gram, how much radiation is absorbed. That's a very, that's a fine measure. It's very objective, very specific, but it doesn't often tell us what we really want to know, which is how dangerous is this? How much are we really being damaged, either damaged or helped by this particular amount of radiation? But to do that, we use another unit called a rem. And if you've heard anything about radiation exposure, or you work with it at your job, work with X-rays or anything like that, you've probably gotten measured in rems, or fractions of a rem. Rem stands for radiation equivalent in humans. So this is specific to humans, and it's just the number of rads above times this specific factor. And the factor tells us something about how dangerous the radiation is. So this discriminates between different types of radiation. Alpha radiation, because it's so massive, is much more damaging than beta radiation for the same amount. So being exposed to a certain amount of alpha particles per gram is going to be more dangerous to you than a certain amount of beta particles. And then, you know, X-rays or whatever you're being exposed to, it's going to change the REM. It's going to change what you've actually been, or the danger that you've actually gotten yourself into. So we always measure, or we usually measure human radiation exposure in REMs or millirems or whatever. Now, to give you some sense of what these numbers look like, a instantly lethal dose of radiation for humans is 500 REMs. So you get 500 REMs of, you can't survive 500 REMs of radiation, or most people, half the people can't survive 500 REMs of radiation, which is 500,000 millirem. I put that in to compare it to what I'm about to show you about. The average for all of us, for people, the average amount of radiation that we're exposed to is about 360 millirem per year. So that's just going around, living our lives. Most of us, on average, are exposed to 360 millirems of radiation per year. That comes from all kinds of places. It comes from space. Cosmic rays and gamma rays get here from space and hit us. We take airplane rides, we get a little bit more radiation, just a little bit. If we get X-rays, CT scans, that kind of stuff, we get a little bit more exposure to radiation. Just like rocks and bricks and stuff like that are always emitting a little bit of radiation, so we're getting some from that. If you live in certain places, you might get more radiation, and not just talking about like nuclear accident places, but like underground type places. If you spend a lot of time in caves, that kind of stuff, depending on where you are, you could be more exposed. If you live at really high altitudes or you take a lot of plane rides, that can increase your exposure a little bit. But generally, this is kind of the average. The upper limit for most people is not to exceed 5 REMs, that's 5,000 millirems per year. So that's like if you were working with radioactive materials or something like that, you would need to make sure to check not to exceed that upper limit, which still is nowhere near the lethal dose, of course. Has anybody here ever worked with X-rays or that kind of stuff in your jobs? Most of the people in my other classes have. What? Studying. Oh, you're studying for it? Okay, so you will. So they have all these various controls. Of course, you want to minimize exposure, so modern X-ray equipment has become much better at making sure that only the thing that you actually want to shoot X-rays at gets the X-rays. It used to be there was a lot of bouncing around and a lot of risk elsewhere, but you'll still see people wear, you know, the lead smocks if you get dental X-rays, that kind of stuff, to prevent any X-rays from getting where they're not supposed to. If you work with X-rays, chances are you will wear some sort of device, and this is true with any of this other radiation also. If you work with radioactive materials, you wear these little devices. They have rings, they have little badges, and they have materials inside that can measure the amount of radiation that they're exposed to. So you would send that ring or that badge in every month to a lab, and they test it and make sure that that ring or badge didn't get exposed to too much radiation. If they did, they'd let you know and say, hey, you've been exposed, we got to check stuff out.
So how do they determine like when a patient has cancer, like how much radiation to use?
Yeah, it's a good question. There's a lot of experimentation there. So they might look at those tumors in labs or in animals and try different doses and kind of see what seems to work. I think there's a little bit of trial and error involved in that it's not, because people are so different and cancers are so different, that it's not like we know exactly this much, we'll do this. There's also risks involved. You know, there's you get burns from the radiation in some of these therapies. So they might start at a smaller dose and kind of see what happens and then ramp it up if it doesn't seem to be working. Those kinds of ideas. I don't know specifically what's known or not about that stuff. I do know that for a lot of these treatments, when you get, especially when they put isotopes into your body, you are producing radioactive material for a while because you're getting rid of this stuff as waste also. So when you do this, you have to go to a special place and you can't really have a lot of visitors because all of you and your waste products are all radioactive. So they have to collect everything and dispose of it as hazardous waste really carefully, and then make sure that before you go home, you're not radioactive anymore.
For regular CT scan or?
No. Like if you have to actually ingest radioisotopes for like iodine, radioactive iodine, that kind of stuff. Yeah. No, not for, if you're just irradiated with radiation, you don't become radioactive from that. All right, so the next part of this then, which ties into this, is something called half-life. Half-life has a couple different uses. Have you heard the term before? Have you ever heard of a half-life? What is a half-life? You know? A half-life is a measure of time. So it's sometimes written as T with a little 1/2 below it. The half-life is the time it takes for half of a substance to decay, to break down. So this is used in, and we're going to talk about how it's used in nuclear chemistry, but it's also used in medicine. When you take a medicine, we're often concerned about the half-life of that medicine, which means how long, in that case it's metabolism, how long does it take for your body to metabolize half of that medication? Something like anesthesia, for instance. If you have like an inhaled anesthesia, like isoflurane or something like that, has a very short half-life, which means that you can control really carefully when it stops working because it's metabolized like immediately. If you turn down the anesthesia a little bit, the person's going to wake right up. Something like a numbing or a local anesthesia, like what the dentist would use in your mouth, has a little bit longer half-life. It takes longer to wear off, right? And so that half-life is a measure of how long it takes for half of it to wear off. If you take some pills, it might say, take it every 4 to 6 hours. Well, that's probably because you want to take as little as possible. And so if the half-life is about 3 or 4 hours, then after that time, about half of it has been metabolized. You still got about half of it in your system, and then it wears off, and then you can take some more. So that's how we think about that. In terms of nuclear stuff, we're talking about how the isotopes break down. So every atom of something radioactive is going to decay. It's going to break down and form alpha particles or beta particles or whatever. Over time, there isn't going to be any left anymore because it's all decayed. So looking at that rate of decay, we look at the half-life. We look at how long it takes for half of the substance to decay. So it looks like this. Let's say we take an isotope. Let's say we have 10 grams of this radioactive isotope, iridium-192. And iridium-192 has a half-life, that's T1/2, remember half-life, of 74 days. So that tells us that it will take 74 days for half of this sample to break down. And we want to know how long will it take until 1.25 grams are left. So how long till 1.25 grams are left? We start with 10 grams. And there's an equation you can use for this. It's a power of 2 thing. We're not going to get into it in this class. If you're curious, go ahead and check it out. the way I like to do this is just to count out the half-lives. So you cut the thing in half, you cut it in half, you cut it in half, you cut it in half, you keep cutting it in half until you get to whatever number you're trying to get to. So in this case, we start with 10 grams. And we'd say, all right, after one half-life, that's 74 days, how much would be left? 5 grams. You cut it in half, 10 cut in half is 5. So after one half-life, there's 5 grams left. After another half-life, another 74 days, how much is left? Yeah, 2.5 grams. So you cut it in half again. So then after another half-life, another 74 days, how much is left? Yeah, 1.25 grams. So you cut it in half again. You cut it in half, cut it in half, cut it in half, and we finally got to 1.5. So how long will it take until 1.25 grams are left? 3 half-lives, or how long in time? Right. So that's 222 days, which is 3 half-lives. All right, so you cut it out. You cut it in half, cut it in half. The only tricky thing about this, that's really all there is to it. The only tricky thing is we often want to see a linear progression. So we want to say, oh, we started with 10. We end up with 1.25. So we divide 10 by 1.25, and that's how long it is. That's not right, because it's not a linear progression. It's half. It's a progression by cutting in half by powers of 2, or powers of -2, technically. So, or sorry, yeah, powers of 2. So we have to cut it in half each time, not just divide it. All right, let's try another one. We can also look at half-life in terms of the amount of radiation, because that's going to be cut in half each time also, just like the mass is cut in half each time. So let's say we have a sample that gives off, of the same stuff, that gives off 8 times 10 to the 4th becquerels. Oh, sorry, not how much, because we're not using grams. What is the radioactivity after 148 days? So it starts as 8 times 10 to the 4th, or 80,000 becquerels. What is the radioactivity after 148 days? Well, we have to figure out how many half-lives is that. So how many half-lives is 148 days of this compound? Did we find it? It's just 2. Each half-life is 74 days. So 2 of them is 148 days. So that's 2. Each half-life for this compound is 74 days. So 148 days is 2 of those periods, of those 74-day periods. 2 half-lives. So that means we need to cut that amount in half twice. So it cuts in half once for the first half-life, and then again for the second half-life. We're not dividing by 2, we're cutting in half twice. So we take this, 8 times 10 to the 4th. And we're going to divide by 2. That's 1 half-life. So now we've got 4 times 10 to the 4th. And then we divide by 2 again. And that gives, or here, I should not use equal signs because it's a little confusing. 8 times 10 to the 4th divided by 2 is 4. 4 times 10 to the 4th divided by 2 is 2 times 10 to the 4th. So after 148 days, the radioactivity is now 2 times 10 to the 4th. So this is a compound that may not be great for something like radiotherapy because it's going to be a long time before all that stuff finally breaks down. That's one of the reasons that technedium ion is used so much, or that technetium isotope is used so much. I'll show you this chart here. Let's put here. So here are some half-lives of some isotopes. And you can see this medically used one only has a half-life of 6 hours. So in 6 hours, half of it's gone. Another 6 hours, another half's gone. Another 6 hours, another half's gone. So within a few days, it's pretty much out of your system. And that's nice for things like imaging when you don't want to have this radioactive stuff around for a long time. That is going to break down relatively quickly. Other stuff can be useful at having really long time scales. For instance, uranium-238, that is not the nuclear isotope. That's like the standard common uranium that we dig out of the ground. And that has a half-life of 4 times 10 to the 9th years. That's a lot. That's 4.5 billion years. So that breaks down extremely slowly. And that's when you hear about, have you heard the term enriching uranium? Like we're worried that certain countries are going to enrich uranium and be able to make a bomb. That's the process of separating this uranium-235 that's used in fission from the uranium-238. It's a very difficult process. It requires a lot of specialized equipment. And so if you can do that, then you can get enough fuel for nuclear bombs and nuclear power plants. But the commonly occurring uranium is not that. So there's nothing dangerous about, or it's still emitting alpha particles, but you can't make a bomb out of that. Another useful isotope is carbon-14. Carbon-14 has a half-life of about 6,000 years. The thing that's nice about carbon-14 is that we're all made out of carbon, and all living things are made out of carbon. So when we are alive, we are continuously taking in carbon and shedding carbon, and all the renewing processes of our body are using more carbon from the environment. But then when we die, all the carbon we have just stays there. I mean, we decompose and stuff, but our bones have the same carbon in them that we had when we died. And so we can see how much carbon-14 is in there based on, or compared to carbon-12, which is the common isotope of carbon. And we can figure out approximately when something died by how many half-lives it has been since then. And that's called carbon dating. So we can see, all right, that's been 10 half-lives since this thing died, so it must have been about 60,000 years old, something like that. Because of that long half-life, it's a lot harder to use carbon-14 to date recent things. Like if something died, if a plant died 200 years ago, we can't really use carbon dating for that to find other ways to figure out how old that is. So here's an example. There's the next page here. Take a look at this one. Suppose a sample is obtained from a prehistoric animal used for radiocarbon dating. We can calculate the age of the bone, or the years elapsed since the animal died, by using the half-life, which is 5730 years. If the sample shows that 4 half-lives have passed, how much time has elapsed since the animal died? If it's been 4 half-lives, how long has it been? Yeah, it's 53, oh, whoops, 57, 30 times 4, which is down here, 22,920 years. So in this case, the half-life is 5,730 years. So if we had 4 half-lives, we'd know that it's 22,920 years. So what does that tell you about the amount of carbon-14 in the sample compared to what it would have been when it was alive 4 half-lives ago? How much carbon in the sample? How much carbon would be in the sample? Excuse me. How much carbon-14 would be left in the sample when it was analyzed? Well, if we figure initially it was at 100%. So then after 1 half-life, it's at 50%. 2 half-lives is at 25%. 3 half-lives, it's at 12.5%. 4 half-lives, it's 6.25%. So you'd analyze the sample and say, oh, okay, this has about 6% of the carbon-14 that it would have when it died. And so we know it's been 4 half-lives or about 22,920 years. So see how that works? Practice some questions like this from your book. Again, we're not going to use the equation, which is what you'd have to use if you wanted to know like how much was left after 1 1/4 half-lives or something like that, like the in-between numbers. We're going to stick to like absolute full half-lives all the time. And so the easiest thing is to count it out and cut in half that many times, and then figure out how much time that is by multiplying by the half-life. Questions about that? All right, so we'll have a quiz on this stuff next Thursday, which means Tuesday we'll start on organic chemistry. Yeah, that works. Little change to the schedule, and I'll post this on Blackboard too. Tuesday, we are not going to do the nuclear chemistry lab, which is the next lab in line. The reason for that is that the nuclear chemistry lab is kind of tedious, but we can also do it pretty easily as a class, just kind of do it all together. So we're going to save that for the very last day of class. We are going to do the organic chemistry lab on Tuesday instead, properties of organic compounds. We're going to do that on Tuesday because the following week is Thanksgiving, and so half the classes don't have labs because we don't have any classes Wednesday or Thursday that week. So that lab is going to be a little bit up in the air. I'm not sure what we're going to do, but I don't want to schedule a lab for that time because we might end up, we'll either use that time for something or we'll just cancel that time. But keep posted on Blackboard. That's for not this coming Tuesday, but the Tuesday of Thanksgiving week. I'll let you know what's going on then. But we're going to do the organic compounds lab on Tuesday. And then the nuclear lab will either be the week of Thanksgiving or the week after that. All right, thanks everybody. Have a good weekend.